Welcome back. Today, we're diving straight into the wonderful world of geometry. But hey, we're not just going to sit here and memorize basic shapes. Instead, we're going to take this one really dense infographic and break it down into a super easy-to-remember framework. We'll be taking this taxonomy of triangles and totally decoding the elegant, highly organized logic that makes it tick.
Here's our roadmap for today. First up, classifying triangles. Second, sorting by side lengths. Third, sorting by angle sizes. And finally, number 4, the triangle takeaway.
All right, let's jump right into part 1, classifying triangles.
So take a look at this foundational chart. At first glance, you just see 6 colorful triangles. But the absolute brilliance of this infographic is how it perfectly splits triangle classification into 2 parallel columns. Right there on the left, we've got a column explicitly labeled based on sides. And over on the right, a column labeled based on angles. This right here is the absolute core to mastering triangles, recognizing that you're always classifying them based on one of these 2 totally independent families of rules.
Moving on to section 2, sorting by side lengths. Now, I want you to ask yourself, how do we actually categorize a shape just by measuring its outside edges? To do this, you kind of have to adopt a perimeter-only mindset. Just for the next few moments, we don't care at all about what's going on inside the shape. We are strictly focused on the length of those perimeter walls. Let's see how this works with our first category.
First up, we have the scalene triangle. The definition here is super straightforward. It's a triangle where absolutely 0 sides are equal. But what's really cool is the visual language the diagram uses to tell us that. If you look closely at that green triangle, you'll spot these tiny black hash marks on the edges. The left side has 1 mark, the right side has 2, and the bottom has 3. In the language of geometry, because none of those hash mark counts match, it's this perfect visual cue that 0 sides match in length. It's just beautifully efficient.
Next, we step up a level in symmetry to the isosceles triangle. This one is defined as a triangle where exactly 2 sides are equal. Notice the visual shorthand again. That blue triangle has exactly 1 hash mark on its left side and a matching single hash mark on its right side, while the bottom has none at all. Those matching marks instantly tell your brain, without needing to see a single number or measurement, that those 2 sidewalls are exactly the same length.
And finally, we hit the peak of our progression with the perfect symmetry of the equilateral triangle. This is a shape where all sides are absolutely equal. Looking at that yellow triangle, you can see how the rule continues perfectly. Every single side shares the exact same single visual hash mark. Total symmetry on the outside edges. So, keeping that perimeter-only mindset, you've got scalene for 0 matches, isosceles for 2 matches, and equilateral for all 3 matching.
Well, that covers our first column perfectly. But what if we just completely ignore the outside edges? What if we look on the inside instead? Let's drop that perimeter-only mindset for a second, because we're about to swap our metaphorical rulers for protractors.
Which brings us to section 3, sorting by angle sizes.
Okay, so the crucial thing here is understanding the math that serves as a foundation for this whole category. Everything, and I mean everything, pivots around the number 90. 90 degrees is our absolute anchor point. As our source breaks it down, acute means less than 90 degrees, obtuse means greater than 90 degrees, and right means exactly 90 degrees. Honestly, if you can just remember that 90-degree anchor, this entire second lens of classification totally unlocks for you. Let's see how this actually plays out.
Let's start by starkly contrasting the 2 extremes. On one hand, we've got the acute triangle. The source makes a really specific point here. For a triangle to be acute, all of its angles must be acute. That means every single interior angle is less than 90 degrees. It's totally pinched closed. On the flip side, look at the obtuse triangle. The rule here is dramatically different. An obtuse triangle is defined by having just 1 angle that is obtuse, meaning strictly greater than 90 degrees. You don't need all the angles to be wide open. Literally just 1 single wide corner changes the entire classification of the shape.
And that perfectly sets up the final category in this column, the right triangle. This is a shape with exactly 1 right angle, a perfect 90 degrees. Now, just like we had those visual hash marks for the side lengths, check out the specific square symbol tucked into the bottom left corner of that purple right triangle. That tiny square is the universal geometric symbol for 90 degrees. It's visual perfection, honestly. You see the square, you instantly know, boom, you have a right triangle.
All right, let's wrap this up with section 4, the triangle takeaway.
So, jumping back to our original diagram, the whole structure is completely demystified now, isn't it? It's no longer just some overwhelming wall of shapes and math terms. You can effortlessly read both columns. You know the left side is the ruler column, where hash marks tell you if 0, 2, or all sides match, and you know the right side is the protractor column, where that magic number 90 dictates whether the angles are pinched, wide, or perfectly square.
But here is the absolute most important thing you should take away from this explainer. These are parallel categorization methods. Every single triangle in the universe has both sides and angles. And what that means is any triangle can be, and actually is, classified by both lenses at the exact same time. For instance, a shape could be an isosceles right triangle, meaning it's got two equal sides from our first column and one perfect 90-degree angle from our second. By separating the rules into the ruler and the protractor, you literally have the tools to define any triangular shape you'll ever encounter.
Which leaves us with this final thought. Now that you're armed with this incredibly useful dual lens framework, I want you to take a moment today to just look around you. Look at the architecture of the bridges you cross, the trusses holding up a roof, or, hey, even the slice of pizza on your plate. How do the rules of side lengths and angle sizes interact to form the structural geometry in your everyday life? The whole world is built on these shapes. All you have to do is choose which lens you want to look through. Thanks so much for joining me today. Keep asking questions, keep looking for the hidden structure in things, and I'll see you on the next explainer.